Welcome back to the deep dive. Today we're tearing up one of the foundational conceptual models we've had for years about how artificial intelligence actually works.
Specifically how these large deep learning models store and retrieve knowledge.
Exactly. For a long time, the thinking was pretty simple. We figured we were building passive calculators.
Nor, at best, extremely fast, exhaustive recorders of associations. A connects to B. Simple as that.
And that default view is just wrong.
Completely wrong. For years, the general public, and honestly a lot of the research community, we all pictured AI memory as this massive digital warehouse, a giant filing cabinet.
But new research is demanding a pretty profound conceptual shift. We're realizing these models are not librarians.
No, they're actually nurturing cartographers.
Yeah.
They're spontaneously organizing everything they learn into geometric structures, literal internal maps of reality.
So our mission for this deep dive is to unpack this research. It completely changes the core insight. Parametric memory isn't a passive warehouse of facts.
It's an active, silent cartographer.
And this radically shifts the focus from simple association, which is really just a lookup function, to advanced spatial reasoning, global navigation. This isn't a small tweak.
No, it changes the entire conversation. It goes from how many facts does it know to how does it structure the relationships between those facts?
Okay, so let's start by contrasting the two competing models. Because for you, the listener, I think understanding this difference is the whole journey here.
Let's do it. First, the one we're retiring, the filing cabinet model, associative memory.
Right. So how does this model handle information?
In this classical view, the AI stores these discrete, local transactional connections. It knows A connects to B, and it knows B connects to C. That's it.
So if you ask it a complex multi-step problem, say, finding a path from A all the way to D.
It has to perform a slow, brute force, step-by-step lookup. It checks A, finds B, checks B, finds C, and so on. It's a very literal sequential process.
That sounds incredibly fragile. I mean, if it misses just one step in that chain.
The whole thing falls apart. Precisely. Now, compare that to the new emergent view, the G plus map, geometric memory.
A completely different approach.
Totally. This model doesn't store individual facts in isolation. It builds a global, integrated map of every relationship all at once. Concepts become points in this internal space.
And related concepts are close together, unrelated ones are far apart, geometrically.
Exactly. So that multi-step reasoning query, what's the path from A to D?
Yeah.
It stops being this cumbersome lookup task.
It doesn't have to check 3 separate connections anymore.
It skips that process entirely. It becomes a simple one-step geometric query, basically a navigation task. The model just sees the shortest distance between 2 points on its map.
It accesses the entire solution in parallel. Okay, that is a beautiful conceptual difference, but how do you prove it? I mean, how do you prove that's what the AI is actually doing under the hood?
Theory needs a brutal test. And researchers at Google and Carnegie Mellon, they designed what they call the impossible path star graph test to really break the limits of that old filing cabinet model.
They set a trap.
That's a great way to put it. They designed this graph structure that associative memory is just fundamentally terrible at solving. Imagine a colossal maze, the path star graph, with dozens of long, complicated paths radiating out from a single central point, the hub.
And the model's task was what, exactly?
Given only the final destination, the endpoint, the AI had to identify the complete ordered sequence of nodes all the way back to that hub.
Which is a problem because simple next token prediction, what these models do, is only built for local prediction.
Exactly. If you're at node 8, you only know about the nodes right around node 8. You have no idea about the ultimate destination 10 steps away.
It's terrible at thinking ahead, or in this case, thinking backward across 10 steps at once.
And that's what they found. When they gave the map directly in the prompt, what we call in-context learning, the models failed spectacularly, often just guessing randomly. The filing cabinet couldn't handle it.
Okay, so failure confirmed the limits of the filing cabinet, but then came the critical pivot in weights learning.
Yes. They stopped giving the model the map in the prompt, and instead, they baked the knowledge directly into its core parameters, its weights.
How did they do that?
Systematically. They trained it piece by piece, encoding every single connection in that maze A to B, B to C, into the model's long-term parametric memory, not just its short-term context window.
And the result, did it just become a better, bigger filing cabinet?
Far from it. The model solved the maze with near-perfect accuracy, even on these massive graphs with 50,000 nodes and paths up to 10 steps long.
Wow.
But here is the crucial detail. The thing that proves it's not just memorization. It could find paths it had never been explicitly trained to find.
What do you mean?
If they train it on path 1 and path 2, it could suddenly generalize and find a new connection between, say, the start of path 1 and the end of path 2, just by navigating its internal map.
Wait a minute. If the model can find novel connections paths that it was never shown, doesn't that mean we have even less control over what it might spontaneously generate? The structure itself is creating competence, not just the data.
It does. And that's the scary side of emergence we can touch on later. But it is just undeniable evidence that the knowledge is stored geometrically. And to confirm it, they essentially took the first photograph of the AI's internal structure.
How do you photograph a concept?
They created a similarity matrix. It measures the geometric closeness of every single concept inside the AI's, its representation space. If the AI was using associative memory, the image should have looked like random static, just noise.
But it didn't.
No. It showed a stunningly clear, unmistakable, bright diagonal line. This line proved that the endpoint of any given path was geometrically close only to the start of that same path. The AI had spatially compressed the entire path into a coherent, organized map.
It's wild. It's like we're looking at the blueprint the system drew for itself. Which brings up the biggest question of all. Why? Why did it spontaneously build a map?
Right. The researchers immediately ruled out the obvious pressures. First, they tested capacity pressure. Was the map just a more compressed, space-efficient way to store all that information?
A simple resource constraint.
No. Proposition 1 in the research proved that both methods, associative and geometric, they consumed roughly the same amount of memory for this task. The model wasn't forced to be clever to save space.
It chose to be clever anyway. Okay, so it wasn't saving resources. What about supervisory pressure? Was the task itself forcing the structure?
Also no. The geometric structure started forming even when the model was only trained on local connections, just A is next to B. It was never even asked to solve the full path, but the structure of the path began to emerge in the weights anyway.
So if it's not external force or resource limits, the answer has to be intrinsic. We're looking at the physics of learning itself. Tell us about spectral bias. This sounds like the secret sauce.
It is. This is where we get into the inherent nature of graph data. Let's use an analogy. A guitar string. When you pluck it, you hear the main note. That's the fundamental wave. But you also hear quieter harmonics that define the tone. The instrument naturally resonates at specific frequencies.
And what are the harmonics of a massive data graph?
Well, a complex graph of facts has its own fundamental structure. Mathematically, it's defined by its low-frequency eigenvectors. These define the intrinsic ways the data naturally wants to organize itself, the strongest underlying patterns.
So the optimization process, gradient descent, it doesn't just memorize the individual facts, it naturally tunes itself to these essential harmonics of the data.
Exactly. It automatically learns the deepest intrinsic structure, the vibe of the information. And because that intrinsic structure is naturally geometric, the optimization process just pushes the knowledge into a map format. It's a consequence of the physics, not a deliberate strategy.
And the spontaneous map-making validates an entire field of research, right? Geometric deep learning, or GDL.
It absolutely does. GDL is the umbrella term for techniques that generalize models to non-Euclidean domains data that isn't neat and grid-like.
Which is most real-world data. We're talking social networks, molecular structures, things that don't fit on a simple XY axis.
Right. They like a common coordinate system. The fact that AI is doing this on its own is maybe the most powerful real-world validation GDL could have asked for. It's proving the theory of the map.
And the engineering blueprint for creating these maps is the knowledge graph, or KG.
KGs are essential. They move us past rigid tables, organizing complex data as triples, like Paris, capital of France. Then knowledge graph embeddings, or KGE, translates those entities into vectors in a continuous space. That is the map.
And once it's a map, finding a missing link is just a simple geometry problem.
Exactly. Let's look at how this is being applied today. Case Study I, engineering the map for reliability with systems like Synalinks and MemGraph.
This is focused on enterprise-grade structure.
Yes. Synalinks is a neurosymbolic framework. It uses KGs to power reliable, factual LLM agents. The biggest challenge in enterprise is getting traceable answers out of messy company documents.
So they take thousands of unstructured reports and manuals and process them.
Yep. An LLM extracts entities and relations, and they store that in a graph database like MemGraph. But here's where the geometry comes in. MemGraph uses advanced vector indexes.
So instead of a brittle keyword search,
it does a similarity search based on spatial proximity. If an agent is looking for project management, but the document said program coordination, The vector index, having mapped both concepts close together, finds the connection instantly.
That makes the LLM much more robust, less prone to hallucination because it's grounded in this structured geometric map.
Precisely. Now look at case study 2, Mind Architect, which applies this to improve human memory. The problem is simple. We forget. Students forget 70% of what they learn in 24 hours.
And the solution uses the ancient method of loci, the memory palace.
Right. Our brains are spatially specialized. We remember things better when they're linked to a location. Mind Architect uses AI to supercharge this, transforming dense documents into immersive, interactive, virtual memory palaces.
That's fascinating. How does the AI generate the spatial blueprint for that?
It analyzes the document, finds the core concepts, and generates a blueprint where each concept becomes a locus or a room, the genetics room, the history room. It uses multimodal AI, like VO, to generate cinematic video and turn abstract ideas into memorable visual mnemonics you can navigate.
The ultimate study guide is now a navigable map.
And if we look at the absolute cutting edge, we have to talk about the space itself. Most of these examples assume Euclidean space, which is flat.
But flat space is limiting for certain kinds of data. If I try to map a branching tree structure onto flat paper, I get distortion.
Exactly. Euclidean space is suboptimal for hierarchical data. You force a complex tree, which grows exponentially into flat space, and you get massive distortion. The concepts at the edges get squished together.
Their relationships become less clear.
Hyperbolic space solves this. Its key property is that it grows exponentially, just like a tree. So models like HyperHKGE, hyperbolic knowledge graph embeddings, can represent those deep parent-child relationships with far less distortion.
It's a map that respects the natural curvature of the data itself.
Yes. And this whole geometric paradigm, it brings tremendous opportunities, but also, as you mentioned earlier, major responsibilities.
Let's start with the opportunity.
Well, first, smarter reasoning. Models solve complex tasks by just seeing relationships. Second, creativity. Navigating a concept space lets AI blend or jump between distant ideas, discovering novel connections.
And it seems we have huge headroom for efficiency. Simply geometric models can sometimes outperform giant transformers because they build cleaner internal maps.
But on the other side, the black box deepens. If memory is a highly interconnected GPS map, altering one fact can unpredictably warp the entire structure.
Editing a filing cabinet entry is simple. Correcting a fault line on a global map is incredibly hard. That makes unlearning information or correcting bias extremely complex.
And that's a huge control and safety issue. This emergent self-organizing behavior is inherently harder to predict and control than a system we design with explicit rules.
Finally, there's scalability and data quality.
Right. Building and maintaining these KGs at scale is a colossal challenge. They are very sensitive to messy, inconsistent data. If your inputs are garbage, the map will be distorted.
So this deep dive has really shown that we thought we were building systems that just look up answers.
But instead, we're creating systems that spontaneously build a deep, geometric understanding of the world. AI is fundamentally an emergent cartographer.
And this behavior emerges not from engineering, but from the fundamental dynamics of learning that spectral bias.
The AI is learning the deepest, most fundamental structure of the data itself.
Which leaves us with a truly provocative final thought for you, the listener. If the AI is spontaneously building this geometric structure based on the natural, intrinsic essence of the data, does this mean that the AI's internal map is actually revealing universal organizational structures that we, as humans, haven't yet consciously observed in our own methods of storing knowledge? Are we learning something fundamental about reality from the maps our machines are drawing?